land degradation problems such as waterlogging and consequently soil salinity. Therefore, the main objective of this work is to evaluate changes in waterlogging, soil salinity, and vegetation cover using remote sensing data. This is the location map of the study area in Egypt and its topography. It covers an area of about 606 square kilometers, and it's about 23 meters below the sea level. I've used 4 Landsat images at different 4 years, which are 1986 and 2000, 2013, and 2019. And I did the image processing, the reprocessing and analysis using the NV software package. Also, I've used 3 spectral indices to study the changes in this land covers, vegetation, soil salinity, and waterlogging. And these indices are the optimized soil adjusted vegetation index developed by remotes, and the normalized difference water index developed by McFaders, and one of the salinity indices developed by Dowie. And these are the equations used for the calculation of these indices. This flowchart also shows the image analysis and map production. First, the Landsat images were radiometrically and atmospherically corrected. Then they were radiometrically corrected, and I've calculated the 3 Landsat indices and the 3 spectral indices. Then I've used a threshold value to create a binary image for each land cover. After that, I made the accuracy assessment with the output results, and I used subtraction methods of these binary images in order to calculate the changes between each 2 consecutive years. And these are the results. I found there is a change in vegetation cover from 1996 to 2019. The vegetated areas were changed from about 20 square kilometers to about 95 square kilometers. This is about 3% of the area, and this about 16% of the area. Waterlogged areas were also increased from about 19 square kilometers in 1986 to about 57 square kilometers, which is about 9% of the area in 2019. On the other hand, some areas or highly saline soils were slightly declined from about 33 square kilometers to about 28 square kilometers. And this images shows the spatial temperature changes in each of the studied land covers. This is the vegetation in each of the studied years, 4 years. And the vegetated area were increasing over time. Also, this is the changes in waterlogging areas from 1986 to 2019. This is the change in SAPCA or highly saline soils in the sewer oasis, and these are the histogram and the values during each year. Also, I made the accuracy assessment. I found most of the studied indices, the overall accuracy was more than or greater than 95%. I changed it also. I studied I made a change detection, studied the changes in each of these land covers between each 2 consecutive years, and these are the values. And here, for example, is the change detection during the whole studied period of time from 1986 to 2019. And I found there is these areas, there is some positive changes, increase in vegetation cover, which checks the green color. And there is areas which has no change in land cover, and this red areas that is decline or negative change in vegetation cover. The same thing in waterlogging areas. The blue means the increase in waterlogged areas, the red means decline in waterlogged areas, and the yellow areas means no change. The same thing with the SAPCA areas. The red color means decline in Sabha areas, while the oily color means increase in Sabha areas, and this is no change. The discussion and conclusion, I found there is increase in vegetated areas over time in sewer oasis, and this was mostly was observed in the last decade. This may be due to the increase or progress in land reclamation and cultivation projects in this area, especially in the northwestern, south parts and northwestern areas of sewer oasis. Also, I found there is increase in waterlogged areas, and this also could be contributed to the increase in agricultural lands, the use of inefficient irrigation systems, also the border drainage in this closed basin, closed depression. There was a decline in Sabha areas, and this could be also contributed to these factors, the previous factors, the increase in agricultural areas, using an efficient irrigation system, and border drainage, which results in the conversion of some of the Sabha areas into permanent lakes. These areas were converted into permanent lakes. I found the use of salinity index also only focus on the highly saline soils, which are called Sabha, because it works only on the spectral range of spectrum, which is the green and red. And therefore, there is a need to make an integration between the remote sensing areas and lab measurements in order to accurately map the low levels and the moderate levels of soil salinity. In conclusion, I found that remote sensing data can provide valuable help in mapping and monitoring spatial temperature changes and vegetation cover, soil salinity, and water logging. Also, I found that sewer oasis is suffering from a serious border drainage, which is due to the increase in agricultural areas, use of inefficient irrigation systems, and border drainage, and therefore there is a need to develop a more effective management program which takes into account the use of more efficient irrigation systems and enhancing the agricultural drainage in the area. Thank you. Do you have any questions?
What is the criteria for choosing the accuracy assessment points? What is the criteria? I think that you put some criteria.
Yeah, I made a comparison between the binary image, the classified image, and the high resolution images, and also the field
check.
Field check. Yeah.
How many points there is?
I don't have them now, but I can give them to you later.
Excuse me, doctor. You use Landsat image only or hyperspectral data?
No, I've used only Landsat.
Landsat. I need to ask you: is Landsat